Yeah, thank you very much. It's a great pleasure to be here for the first time mathematically. So I'd like to tell you about a paper with Iram Portakal. She was a postdoc with us. She's now in the statistics group in Munich. And the title is, whoops, so the title is Geometry is really going to be algebraic geometry, a little bit of combinatorial geometry, but mostly algebraic geometry. And equilibria are supposed to be understood in the sense of game theory. And this is a quadratic surface in a tetrahedron. So let's see how it goes. So I'm going to start out with some basics from game theory. And so this is going to be a game with n players in normal form. And the ith player has di strategies to choose from. So they're called, I'll just label them 1 up to di. And the game in normal form is given by n payoff tables. These are actually tensors. And each payoff table, so the ith payoff table for the ith player, and they all have the same format. So it's a tensor of format d1 by d2 by d3 by dn. And the interpretation is that this payoff is a real number, positive, negative, or 0. And so the entry in the ith table in position j1, j2 up to jn is the payoff which the ith player receives. Well, if everybody makes their choices. So if the first player chooses strategy J1, player 2 chooses strategy J2, and so on. Right? So this is the interpretation. So a game is given by n payoff tables, and these are really n-dimensional tensors filled with real numbers. Now, just by way of example, so if n is 2, now this is a 2-player game. And in this case, we'll do binary choices. So we discussed over coffee, so not to use gender, but I'm going to choose Bach or Stravinsky. So a couple would like to attend a musical concert, and the choices are either attend Bach or Stravinsky, but they have a strong preference of going together, right? So the payoff tables here are 2 by 2 tensors, that is to say 2 by 2 matrices. And the first person has a slight preference for Bach. The second person has a slight preference for Stravinsky. So the game is given by these 2 matrices. So a 2-player game is given by 2 matrices. An n-person game is given by n tensors. Now, how will they make their choice? Well, the solution will be a mixed strategy. And a mixed strategy is a probability distribution, non-negative real matrix, here in this case, a 2 by 2 matrix. And the entry Pij is the probability that player 1 chooses consort I and player 2 chooses consort J. So this is a 2 by 2 non-negative matrix whose entries sum to 1. So this is the setup of a game. Now, the choices really are probabilistic. So think about the players as random variables, and their state, these are discrete random variables with finitely many states. So bracket D1 is the set of the first DI, D1 positive integers. So every player is a random variable. And then the players collectively choose a mixed strategy, which is a joint distribution, a joint probability distribution for these states. Now, the distribution, again, is a tensor of the same format. The entries are positive numbers. I will assume today, for simplicity, that no 0 entries, that all probabilities are positive and they sum to 1. So again, the interpretation, so the Pj1 up to Jn entry is the probability of the event that the player 1 chooses J1, player 2 chooses J2, and so on. Now, what's in it for the player? Well, they will receive a payoff. And since it is probabilistic, there is an expected payoff. So the expected payoff for the ith player is the dot product of the vectorization of the payoff table and the vectorization of the distribution. So I'm simply take the product of corresponding entries and multiply them up. And so this is the expected payoff. So I'm fixing the game is given by these x's. Then I have some unknown distribution. and that needs to be specified, and this will be the expected payoff. So each player wants their expected payoff to be as large as possible, right? That's the game, right? So how to make everybody happy? Well, you make people happy. Presumably, you want to reach some equilibrium. So there is some notion of equilibrium that will make you happy. I'll give you the formal definition in a moment. So let's summarize. So I'm given a fixed game. So I'm given a list of n payoff tables, each of which is an n-dimensional tensor. We're going to be interested in the set of all equilibria, according to some definition of equilibrium, and that is a subset of the probability simplex of dimension d1 times d2 up to dn minus 1. Right? This is the set of equilibria lives inside this high-dimensional simplex in our tensor space. So those are the probabilities. Now, how do you define an equilibrium? So this is the definition we're going to be using today. So the talk today is about dependency equilibria. And to define this, I need one more definition, namely conditional expected payoff. So I introduced on the previous slide the expected payoff, but now we're going to look at the conditional expected payoff of the ith player. And the condition is that this should not depend on her choice, right? So conditional expected payoff for any given player should be independent of their choice. So let's say this in formulas. So here's the formula for the conditional expected payoff. So I'm conditioning on the ith player making choice K. So the ith player called Janos has, DI possible companies to invest in, right? Google and Amazon and Tesla. And you're choosing Tesla. That's it. So the conditional expected payoff for everybody is conditioned on Janos choosing Tesla for his investment. Okay. So then, okay, so it's the same formula, except I take this sum out. I'm summing over all the other states. So this notation P plus plus K plus plus. So this is simply the sum of all table entries. So it's simply the probability where Janos fixes Tesla, right? Summing out everything else. And then otherwise, it's the same formula. And the algebraic equation is that Janos choosing K should have the same conditional expected payoff if he chooses K prime. So we require this equation for all players I and for any pairs K and K prime of stock choices. Okay. Now let's clear denominators. So if we clear denominators, this will be a homogeneous algebraic equation of degree 2 in the P's, right? So you have a ratio of P's, you have a ratio of P's, so clearing denominators, you get a system of quadratic equations. So I'm going to be interested in the solution set of these equations. And being an algebraic geometer like Andras, we're going to do this in a complex projective space. Okay, so I'm now going to look at the vector space of complex tensors. We're going to use the corresponding projective space. I'm going to find the Spohn variety to be the zero set of all of these quadratic equations. I want the solution set to these homogeneous quadratic equations. So algebraic geometry is the study of zeros of polynomials, and I mean it. I want to study the zeros of these polynomials. Now, I know there's a lot of people interested in probability here, so let me make a comment about using algebraic geometry for applied problems in the real world and elsewhere. So typically, we're given a system of polynomials, equations, and inequalities, and in the application, this is over the real numbers, and we want to understand these solutions, right? Now, that's a very difficult problem. So in applied algebraic geometry, we make the problem easier. We relax the problem in 3 steps. First step, throw away all inequalities. Now that makes the problem easier, right? Second step, replace the real numbers by the complex numbers. Now that makes the problem certainly easier because now polynomials always have roots, right? Now third step, you replace affine space by projective space. Now any 2 lines in the plate will meet. Any 2 conics meet in 4 points, right? So after those 3 steps, after you transition to complex projective space, now problem is easier now you're in a setting where algebraic geometers can actually maybe make a contribution. Of course, at the end of the day, in a real world application, such as molecular biology, you have to go back and deal with real numbers that are non-negative and so on, but I'm not going to do this. I'm going to focus on the zeros of these quadratic equation solutions. Now, many of you will maybe be familiar with the concept of Nash equilibria. And so the proposition is that the Nash equilibria are dependency equilibria of rank 1. Remember, P is a tensor, right? And a tensor has a rank. Now, you all know the rank of a matrix, right? So a matrix has rank 1 if it's a product of a column vector and a row vector. A tensor of rank 1 is the same thing, except you have more dimensions, right? So if you take the outer product of a bunch of vectors, you get a rank 1 tensor. And if our tensors have rank 1, then that corresponds to complete independence. And those are the Nash equilibria. So geometrically speaking, the set of Nash equilibria is the Spohn variety intersected with the Segre variety, and Segre variety means rank 1 tensors. Okay. Now, there are two ways to think about this proposition, right? Either you knew what a Nash equilibrium is before you walked into the room, and that's a proposition. If you didn't know what a Nash equilibrium is before you walked in, it's a definition. Okay, so it's either a definition or a proposition. Now let's recall briefly a few facts about Nash equilibria. So a very important theorem due to John Nash, proved in 1951, is they always exist in the closed probability simplex. So based on fixed point theorems, Nash argued that every game whatsoever has at least one Nash equilibrium, and therefore at least one dependency equilibrium, right? Because dependency equilibrium are more general. Now, to find the Nash equilibria, you need to solve equations. These are polynomial equations, in fact, multilinear equations of degree n minus 1. Now, that's important, right? Because if n is 1, these are linear equations. So studying two-person games is the subject of linear algebra. Now, of course, there's still complexity that comes from the combinatorics, right? Because depending, whether the entries are 0 or not, there's a very difficult combinatorial problem. But for two-person games, the combinatorial structure is the difficulty. The algebraic structure, it's easy. It's linear algebra. Now, my group at the University of at Leipzig, Max Planck Institute, is called nonlinear algebra. So I like to go from linear algebra to nonlinear algebra. So that's why I'm interested in games with more than two players. Now, the number of these solutions is, as Bernstein's theorem, is a certain mixed volume of simplices. And this was first discovered by McKelvey and McLennan. A lot of these papers are in economics journals in the late 90s. There's an important paper by Datta. So she proved that the Nash equilibria are universal. So every semi-algebraic set is the set of Nash equilibria of some game with 3 players. So if you can think of your favorite system of polynomials and inequalities, say with integer coefficients, then I can make a 3-person game such that your solution set is my set of Nash equilibria. Okay. Now, I looked at this almost 20 years back. I wrote a little booklet called Solving Systems of Polynomial Equations. And one chapter was called Polynomial Systems in Economics. And I think this is still a nice brief introduction to the subject. So here we're talking about the equations that define Nash equilibria. Then the mixed volume arises. It counts the number of solutions. And then how you actually find them with the numerical packages that were the state of the art 20 years ago. Okay, so this is a quick review of Nash equilibria. Are there any questions? Please interrupt me if there's questions. Okay, you said there are no questions, so that's good. No questions. Okay. Now here's the picture again. So this is the picture of the Segre surface, right? This is the picture of 2 by 2 matrices of rank 1. Now these are 2 by 2 positive matrices whose entries sum to 1. That's called a tetrahedron. And then inside this tetrahedron, the matrix has rank 1 if the determinant vanishes, that is to say P11 times P22 equals P12 times P21, and this is the Segre surface, right? So Nash equilibria arise when players make independent choices, and this is the independent surface. So I introduced dependency equilibria on tensor space. And then the rank 1 tensors, the independent situations, give us Nash equilibria. But of course, there are many other models. There are many other ways of specifying equilibria. So Nash is the most popular one. And this is a very, very interdisciplinary game. So game theory is studied in mathematics and economics, statistics, certainly. And in recent years, most of the literature has been in computer science. A lot of the game theory papers are in computer science, conferences more so in computer science. But there's one more field that I like to mention, and that's philosophy. And that is because Nash equilibria can have undesirable or counterintuitive properties. And this is also a concern in philosophy. So things like prisoner's dilemma is a dilemma for philosophers. And our work follows a beautiful article by Wolfgang Spohn called Dependency Equilibrium. So he's a prominent senior philosopher, and he published this paper in Philosophy of Science. And here's the definition again. So the conditional expected payoff of each player is independent of her choice. And Spohn argued that from his point of view, that this is a good notion of equilibrium. And that's, recall, that's why I call this the Spohn variety, right? So the Spohn variety is the complex projective variety, it's the complexification of the set of dependency equilibria, and Spohn is Wolfgang Spohn, philosopher from Konstanz. Now, I already pointed out that dependency equilibria require nonlinear polynomials of degree 2, even for 2-player games. So Nash equilibria are linear, have a linear description, but dependency equilibria, even for 2 players, are quadratic. And Spohn himself offers the following warning about nonlinear algebra. So in his paper, he says, the computation of dependency equilibria seems to be a messy business. Obviously, it requires one to solve quadratic equations in 2-person games. And the more persons, the higher the order of the polynomials we become entangled with. All linear ease is lost. Therefore, he says, I cannot offer a well-defined theory of dependency equilibria. So it's this warning, precisely this warning, that makes them interesting to me, because I'm interested in nonlinear algebra. It's precisely the nonlinearity. It's precisely that we're not talking about linear spaces, but varieties that makes it interesting. Right? So that's why this is called the Spohn variety. Now here's the original source. It's absolutely beautiful to read philosophy papers. There's essentially no formulas, right? So he goes, in this note, I would like to present and briefly discuss a new equilibrium concept for game theory. When it occurred to me 24 years ago, I put it aside because it seemed to be of doubtful sense. And then he goes on about the prisoner's dilemma, and he introduces dependency equilibrium. So this is the paper that inspired us, Irem and me, to follow this topic. Now, of course, for me, these are algebraic varieties. They are determinantal varieties. So this is, again, from Stone's paper. So now we took this and we turned them into matrices and rank conditions. So what I'm going to do now for each player I, so I is from 1 up to n, I'm going to define a matrix that's very tall and skinny. It's going to have di rows and only 2 columns. And in this matrix, in the first column, I simply put the marginal probabilities that just the probabilities for Janos' choices, right? So in the kth row, I put the probability that he chooses company K. And in the second column, I'm going to put the numerator the corresponding numerator of the conditional expected payoff, right? So I'm separating the numerator and the denominator. I put the denominators in the first column and the numerators in the second column. I'm going to call this matrix MI. Well, by definition, dependency equilibria are points where each matrix MI has rank 1. So the clearing of denominators I alluded to 11 minutes ago says that this tall and skinny matrix is a rank 1 matrix. Let's see an example. So if I have a two-person game, so the first person has a payoff matrix, a 2x2 payoff matrix with entries Aij. The second player has entries Bij. Then my matrices look like this. So here in the first column, I have the row sums and then the corresponding numerators. Here I have the column sums and the corresponding numerators. And the Spohn variety is the point in P space in projective 3 space, which is the complexification of our tetrahedron. And it's defined by the constraint that both matrices have rank 1. That is to say, the determinants of both matrices are 0. Okay, so it's a curve, right? It's given by two quadratic equations. So I have a curve in 3 space given by the first quadratic equation and the second quadratic equation. So what can we say about a curve that's the intersection of two quadratic surfaces in a 3-dimensional space? Well, let's compute this for Bach or Stravinsky, right? So for the first player, we get this matrix M1. For the second player, we get this matrix M2. So there is a unique Nash equilibrium. Here is the Nash equilibrium. It sits right in the middle. So I need to solve a system of 2 quadratic equations and 4 homogeneous variables. Now, what does that mean? Well, if you take the commutative algebra class tossed to American kids tomorrow morning, you calculate the primary decomposition of this ideal, right? So I look at the ideal generated by my 2 polynomials. It breaks up into 3 components. So this ideal is the intersection of 3 prime ideals. One of them specifies a line. So S and B are Bach and Stravinsky. So the first component is this line. Then here, this is another line that cuts right through the middle of the tetrahedron. And then finally, here is another quadratic curve that sort of straddles the boundary. It doesn't meet the interior, right? So in this case, the only piece that meets the interior is this last line. It goes right through the middle and it pierces the Segre surface, our beautiful surface, right in the middle. Its unique independent point is the Nash equilibrium. That was the definition of Nash equilibrium. So down here is the Nash equilibrium, but then in this case, the entire segment is the set of dependency equilibria, but then the entire black complex projective curve is the Spohn variety. Now, this was a very, very special game, but in general, this will be an elliptic curve. So the intersection of 2 quadratic surfaces in 3 space is a genus 1 curve. It's an elliptic curve, the kind of curves that your friends in cryptography like. Now let's look at 3 players. Suppose I have 3 players, each of whom has a binary choice. So n is 3 and D1, D2, and D3 are 2. Let's call the players Adam, Bob, and Carl. So they have 2x2x2 payoff tensors. So A for Adam, B for Bob, C for Carl. Then here are the matrices. You know, you have these denominators. You have the corresponding denominators. Now the Spohn variety is cut out by 3 quadratic equations in the 8 homogeneous coordinates of a 7-dimensional projective space. And these coordinates are called P111, P112, P121, P122, P211, P212, P21, no, 2, whatever, P222, right? So those are the entries. Those are the names of the homogeneous coordinates in our 7-dimensional projective space. Now, to get the Nash equilibria, we now intersect with the 3-dimensional Segre variety. So rank 1 tensor, this was the thing I acted out, right? I acted out these 3 projective spaces in my P7. And this corollary is taken from the book from 20 years ago. So So now if we choose local coordinates on each of these lines, I'm going to call these local coordinates A, B, C. And the set of Nash equilibria are just the common zeros, and this is just the way of reinterpreting this. Right? Okay, now let me give you a first theorem. So this talk lasts about 55 minutes, and we'll have two theorems. This is the first theorem, maybe three. This is a not so difficult theorem. So now let's fix generic payoff tables. So now X is the game. X is the list of n-dimensional tensors. And generic means random in algebraic geometry. The entries are picked at random. Right? So with probability 1, this will be true. Or outside, we're outside some algebraic hypersurface, this will be true. So the Spohn variety is always irreducible in this general sense. Its dimension or codimension is the expected codimension, and the degree is expected, right? So the codimension is d1 plus d2 plus dn minus n, and the degree is just the product of the number of choices for the players. Now, again, in applied algebraic geometry, a variety walks into the door. So a variety walks into the door. The first question you ask him or her, what is your dimension? How many degrees of freedom do you have? The second question you ask that variety is, what is your degree? How curvy are you? Do you have degree 1? Are you a linear space, or are you more curvy, right? So the first question is dimension. Second question is degree, and here the situation is as expected. Now, in this generic Bach-Stravinsky situation, as I said, we have an elliptic curve. An elliptic curve famously is not a rational variety. An elliptic curve cannot be parametrized by polynomials or rational functions, but in all other cases, it's rational. All other cases, it's a rational variety, and I'm going to explain the geometry. So it's a map onto this n-dimensional space with linear fibers, P1 to the n. Again, here is the equational description for 3 players, each having 2 choices. We simply make the determinants vanish, and we get 3 homogeneous quadratic equations whose 8 variables I try to recite in a tongue twister. Now, to lead towards the second theorem and to lead to combinatorial geometry and matroids and all that, let me define the payoff map. The payoff map, so remember we have the fixed game, and let's say we have some probability distributions. This may or may not be an equilibrium. So the payoff map takes this distribution and maps it to the vector of expected payoffs. Let me write xi, little xi, for the expected payoff. Remember, this was the dot product of these 2 long vectorizations. Now then, for each Spohn equilibrium, for each point of the variety, if I take my tall, skinny matrix mi, and I multiply with the column vector xi minus 1, then I get 0, right? That was the definition. Remember, in the first column, I had the denominators. In the second column, I had the numerator. That's all I'm saying. All I'm saying is that I have the numerators and denominators. So in particular, this matrix has rank 1. Now, the payoff map records each player's expected payoff, but I'm going to look at this in the compactified setting of a product of projective lines. So I have this map. So dash, dash, dash means it's a rational map. It may not be defined everywhere. And I simply take my point P upstairs in the Spohn variety, and I map it to this vector of length n, the kernels of these matrices. And Zi is so I'm using homogeneous coordinates for the iso. Now here comes a key idea, right? So let's look at this expression, mi of P times Zi transpose. Well, that's linear in P, but it's also linear in Zi, right? But if I have a bilinear expression, if I have a column vector that depends bilinearly on 2 things, well, there are 2 ways of writing this as a matrix vector multiply, right? I can either take the matrix and fill it with p's and multiply with the z vector, Or I can make some other matrix. I fill it with the Z and I make P the column. Right? That's just. Now this matrix now has more columns than rows. It has DI rows and D1 times D2 times DN columns. Its entries are binary forms in ZI, and as I said, the P is now a long column vector. Now the final step, I'm going to take these matrices and I stack them on top of each other. So the first player has a matrix, I put it above, then I put the second matrix below it. So I stack these K matrices one of each other, and then the resulting matrix I call the Konstanz matrix. So Konstanz is a city in the south of Germany, almost Switzerland. You can spit to Switzerland if you wish. And that's where Spohn is from. So we're using the guy and a city. So, okay, now what about the Konstanz matrix? Well, the rows are linearly independent if I specify generic proposed payoffs. So therefore, the kernel has dimension number of columns minus number of rows. Now, with this setup in mind, I can rewrite the Spohn variety. The Spohn variety is the set of all tensors such that the P is in the kernel of the Konstanz matrix for some payoff vector Z. So there exists a payoff vector such that I'm in the kernel. That's equivalent to the Spohn. Let's see an example. Right? Now this kernel dimension, so it turns out that this is a non-negative number. Okay. So now it's been a long afternoon, right? So I have a bunch of positive integers that are at least 2. Okay. I'm saying their product is greater or equal to their sum. Now, could they be equal? Yes, they could be equal if they're both 2. Okay, so that's the only case, right? So if D is 0, then of course that can only happen if I have 2 numbers and they're both 2. In this case, the Konstanz matrix in affine coordinates is this 4x4 matrix, right? Now the determinant is a curve of degree 2, 2 in the on the 2 lines, right? So x1 is an affine coordinate on this payoff line. That's the expected payoff for the first player. x2 is the affine coordinate on the second line. But now the payoff map gives a birational isomorphism from this elliptic curve from Vx to this elliptic curve. So elliptic curve, the way you learn it in your beginning algebraic geometry class is a cubic curve, sadly presented to you in Weierstrass form, but it's also a 2 degree curve in the product of these two. Now, in all other situations, if you take the product of integers at least 2, it's bigger than the sum of those integers. And so in this case, capital D is at least 2. So in this case, the map will be dominant, pi x, the payoff map will be dominant, meaning onto in the setting. And the generic fiber is a linear space of dimension D. But again, interpreted projectively, it's a projective linear space of dimension D minus 1. And summarizing everything on this slide, we've shown that the Spohn variety is birationally isomorphic to the base times the fiber, right? So I have the base, which is the payoff space. I have linear fibers of the constant dimension. And so therefore, I've shown it's birational. Right? So in this case, it's an elliptic curve. It's not rational, but in all other cases, I've given you a parametric representation of the Spohn variety like this, and it's parametric over specified payoffs. Now this brings me to the second theorem and to combinatorial geometry. Right? But before I do that, let me do one more example. So I call this philosophy meets Del Pezzo. So for example, this is a nice case. So if D is 1, then so if you have 2 integers where their product is bigger by 1 than their sum, they must be 3 and 2. So in this case, the Konstanz matrix is this 5x6 matrix. So A is the payoff values for Adam. B is the payoff values for Bob. Now the parametrization now takes the payoffs, right? So you specify the payoffs. Now you're interested in all the games where Adam expects payoff x1 and Bob expects payoff x2. And we map this to the kernel of the constants matrix, this matrix, and this kernel lives in as a unique point in P5. Now this parameterizes the Spohn variety, and the inverse of this map is the payoff map. Now this is dash dash because there are precisely 6 points where the rank drops below, right? So this is a 5x6 matrix. There are 6 points where the rank drops to 4. In this case, the kernel map is not uniquely defined, and algebraic geometers call this a blow up, right? So for Andras, we're blowing up P1 times P1 at 6 general payoff points, so we get a Del Pezzo surface of degree 2. Now, for everybody else, what I'm saying is the payoff values in this example determine a unique equilibrium, right? So if I specify, I say that your payoff is 17 and your payoff is 12. In this example, there will be unique equilibrium. Okay, so the payoff region is the image of the set of dependency equilibria under the payoff map. So for example, for this 2x2 game, I take this set of dependency equilibria, it gets mapped by the payoff map. The payoff map is a linear map. So I have this polytope. So I map the simplex under the payoff map. It maps the polytopes. In this case, the tetrahedron gets mapped onto the yellow triangle. And then the variety gets carried along for the ride. In this case, this blue line is the payoff region, but in general, in all other cases, it's full dimension. Let's look at this. So this is the payoff region for the 3x2 game. Del Pezzo meets philosophy, right? So this is the payoff table. So this is the x-axis is the payoff for the first player. The y-axis is the payoff for the second player. So I fix some particular game. So my 5-dimensional simplex gets mapped into the plane onto the pentagon. So the 5 vertices get mapped here. So I have this yellow pentagon. And then inside the pentagon, I have the actual payoff region. And in this case, the payoff region is the union of 2 blue curvy triangles. Now, if you're in the interior of these triangles, and over this stratification, I have a bundle of polytopes, right? Because I have a fiber. The fiber is a linear space, right? And then if you intersect with the simplex, then you get the polytope. Now, this works fine, except at this point here, the fiber drops rank. So this is one of the 6 points that gets blown up. So there, the dimension will be higher. So here's the second theorem. It's a theorem about oriented matroids. So the payoff region for a generic game is a union of oriented matroid strata in Rn. Now, oriented matroid stratum says that I have a rectangular matrix and I prescribe the sign of each maximal minor. 30 years ago, this was called chirotope. Andreas Dress called it a chirotope. So, okay, so I'm prescribing for the constants matrix. All I'm saying is I'm specifying the sign, positive or negative, for every maximal minor. And those are the regions here. So the regions that you here see, and the boundary is a union of irreducible hypersurface of a certain degree, roughly the sum of the di minus n plus 1. Okay, so I have in payoff space, I have a stratification. I know the algebraic boundaries, and I can describe the actual payoff region. And this is sort of a nice example where we have the complex algebraic geometry driving the situation. This is the P1 times P1 that gets blown up toward the Del Pezzo surface. But once we look at real numbers and the inequalities they satisfy, then we get these regions. Okay, so this is the situation. Now, a more interesting game. So here's Adam, Bob, and Carl again. So they have a 2x2x2 game. So in this case, the constants matrix is a 6x8 matrix. There are 28 maximal minors. It looks like there are equations of degree 6, but they actually drop to 4. So have an arrangement of 28 quartic surfaces in 3 space. And this is the same picture as before, just 1 dimension higher, right? So a quartic surface for an algebraic geometer is called a K3 surface. So have an arrangement of 28 K3 surfaces that bound various blue regions, and that's the payoff region. Now, the reason Spohn, the philosopher, was very, very interested, he was interested in Pareto optimal points. So he wanted to have Pareto optimal points. So Pareto optimal points are sort of on the upper right margin here, where the expected payoff is sort of optimal for both players. So Pareto optimal means you cannot increase, you know, x1 or x2. You're sort of at the upper rim. And so this gives a concise algebraic description of a Pareto optimality. I realized I spoke a little too slow, so I'm going to stop the quiz. I'm going to go over this. So, you know, philosophers, of course, what does all this mean? Let me end briefly to say a little bit about statistical models, and then I'm going to wrap up. So we looked at Nash equilibria. They are defined by complete independence. The players are completely independent. They make their choices, and dependency equilibria, where the players are tied together. But of course, we can have any kind of independence or conditional independence situation in between. So a conditional independence model, CI model, is specified by a finite list of statements. A is independent of B given C, where A, B, and C are pairwise disjoint collections of players. So our choices are independent of what happens in the last row. That's what I'm saying. Now, for any such a CI model, I can define the Spohn CI variety simply by intersecting the Spohn variety with the model, the variety given by the conditional independent statements. So for example, if C is a set of all conditional independent statements, then I have complete independence, and that's the Segre variety, and I get Nash. It's kind of fun, actually. I mentioned earlier counting the number of Nash equilibria is a nice mixed volume calculation for binary games, and I'm going to here assume for the rest of the talk the game is binary. The number of Nash equilibria, expected number, is the number of derangements, 1, 2, 9, 44. What's the probability of getting your hat back at the hat check? Although most young people these days don't wear hats when they go out. Now, beyond Nash, even the case of one single edge is interesting, right? Suppose you have n players, and they're all independent except for 2 players. Those 2 players are linked by an edge. So it's like the most trivial network. That already turns out interesting. So in this case, MC, the model, is this Segre variety. So I have copies of P1 for all these independent people, but the 2 players that talk to each other, they form a P3. Now I'm 1 dimension above Nash. So this is an n+1 dimensional model. So the Spohn CI variety is a curve. And Ira, my co-author, together with the student, actually wrote a very nice paper just about this case, and they're working on a generalization. Now, in the last 4 minutes, so what did I do today? So I presented a new direction and at the interface of algebraic statistics. This was sort of a very, very brief glimpse to algebraic statistics, and there are many, many, many open problems. Now, these kind of models, these Bayesian networks, are very important for causal inference. So I should maybe say a causal inference is a very hot topic in statistics, right? So you have maybe data that say that smoking and cancer are correlated, but what you want to know is whether smoking causes cancer or whether cancer causes smoking, right? So you want to just based on data alone make that inference, and here we're tying this together with this Bayesian network structure on the graph. And it's actually kind of fun to go back and look at Spohn's paper. So Spohn wrote another paper called Dependency Equilibria and the Causal Structure of Decision and Game Situations. So in this paper, he introduces dependency equilibria, Bayesian networks, and many, many more things. And he talks about causal graphs and Bayesian networks. And this paper is from the 1990s. So people who study causal inference nowadays reference a gentleman named Judea Pearl, who was very influential, but actually Spohn had the same concepts in philosophy at the same time. So we found him to be quite inspiring, and that's why there's the Spohn variety, and it's birational parametrization by the Constance matrix. That's the end. Many thanks for listening. Exactly. So it's a larger set. So it's a more inclusive set. There are many other notions. So there's also correlated equilibria. So there are many generalizations of Nash equilibria. Now this one turned out to be the one that Spohn suggested, and we like it because it has a nice algebraic geometric structure. So yes, so in his papers there's a discussion. So there's an analysis of a number of games, like like for example, there's sort of chain games where people have sequential moves, but in particular, the point of departure was prisoner's dilemma. So he offers an analysis of prisoner's dilemma using this setup that's more convincing for the philosophers. Well, the thing about semi-algebraic sets, they can be rather complicated, right? The variety itself, now the variety itself, of course, as I said here, yeah, so the variety itself is a rational variety. I think it could be complicated, but you have this sort of bundle representation, right? You have this matrix representation, and based on this, I think one should be able to study so I think there's the complex geometry that's already interesting, but then of course in the application we're interested in real numbers. But yeah, I think it would be nice. So this is very new. I think there are many questions. I think it would be nice to study this from a topological point of view. I mean, exactly. So let's go back to this picture. So here's what I'm saying, right? So I have this variety that's upstairs. So as a complex variety, it's this K3 surface, right? It lives in a high dimensional space. I have a payoff map from the surface onto this plane. Now, of course, the real points will map to real points. So it's sort of, generically 1-to-1, except at 6 points. But of course, in the application, we're interested in this blue triangle and this blue triangle, right? This is where the fiber upstairs, we have actually positive distributions. So there's sort of 3 stages. There's the complex geometry, and there's the real numbers, and then there's the real non-negative numbers. And the blue stuff, is what you get if you're interested in the real non-negative numbers. Yeah, that was a bit too fast. So that was, yeah. Yes. So so all I was saying is that was too fast. So all I was saying, we have a notion of conditional independence models. There's no causality yet. But based on this, based on conditional independence models, there's now a new class of models that are called causal models, where you have an additional structure that you hope to learn, called causal structure. And the point I was making, it was a bit too fast, was here all I'm doing is I'm putting additional conditional independence among players, right? I'm saying these players are independent given what happens. Now, in addition to this, I could also ask for causal structure, right? So you're influencing me rather than I'm influencing you. And the only one reason I brought this up is because, another work of Spohn, this also came up. So you had the insight that one should connect game theoretic notions with statistical notions, including causality. We have so there are some articles. There's some recent work in algebraic statistics at the interface with causality. It's in the beginning, but it's very interesting. Very interesting. Yeah. And here we focused on conditional dependence, but of course, among these conditional dependence are also the rank strata, right? And so this would be, you could set up the model so it specifies rank 2 or rank 3. We don't know. I mean, I said here, even this case of a single edge is very interesting. So these guys on the ball, he's a very smart PhD student, but it's very much the beginning, right? So I have this Sporn variety, and I can intersect it with any interesting variety in tensor space, including rank 2 tensors. That would be very interesting. So this would be saying, right, I have these players, and they are independent of each other, conditioned on something else, right? There's one binary random variable, whether it rains or not, right? So if it's on a sunny day, they're completely independent. But on a rainy day, they're also completely independent, but it depends on whether it's sunny or rainy. That's how they make their choices. We're working on it. Now, yeah, exactly. I mean, this is, of course, whenever you deal with the people in other fields, then you have to go back, right? So we took his material, we did some math out of it. Now, of course, the conversation has to go back. So Irem just wrote one of these fancy proposals in Germany, the Emmy Noether grant, and she hopes to go to Constance and work with him. But this takes time. I mean, going back and communicating with the people in another field, this obviously takes a while. I mean, we sent in the paper we discussed, but we turned this into math. We turned this into algebra.